Okay. Good afternoon, everyone. Thank you for coming. Now, turn. Going to share with you a research work during this year in WinLab. The topic I'm going to talk about is on the scalability of ad hoc wireless network. First, I will introduce the motivation of research on ad hoc networks, including the problems with current technology and the research approach I'm going to take in my work. And my work is focused on the scalability, the mechanisms for improving system performance and scalability of ad hoc wireless networks. And the first approach is the use of a hierarchical architecture. The approach I have adopted include both analytical and experimental. We will discuss about the results of both approaches. And the second approach is the use of a cross-layer adaptive routing. And we will talk about the adaptive routing framework and a 5 MAC aware routing metric. Finally, I will conclude my work and highlight the future work. The ad hoc network is a peer-to-peer network which allows a group of users to communicate and work collaboratively. And the ad hoc wireless network, it has been used for military communications from early 80s of last century. The early products are for the specialized tactical applications and sensing applications. And ad hoc radio technique has migrated to commercial scenarios such as mesh and sensor networks. And the current technology are for existing telecom markets. And more companies start to provide multi-service for as a mesh network for industrial and metropolitan applications. And give you an example. This is a mesh network which can be deployed in the city to provide ubiquitous wireless coverage for internet access, video surveillance, and use as a network to provide for use as the first responders, such as the police, firefighter, and medical services. And it is expected the rapid deployment, cost benefits, high link speed, and low power consumption will be of benefit of broadband access and wireless communications. While ad hoc networks offer rapid deployment and cost benefits, we know that the performance is not very good as expected. I have summarized some problems with current technology. The poor scalability caused by multi-hop transmissions, which has been pointed out by previous work that the throughput of per node can only be dropped dramatically as the number of nodes in the network increase. And when there's a significant fraction of traffic have to be routed to a host in the internet, the scaling problem becomes more difficult. In a wireless network, the topology change would increase the routing overhead. And this is the simulation result showing that the routing overhead increase when the node mobility speed increase. Therefore, the scaling problem associated to ad hoc routing is also a problem. The inefficient routing, the ad hoc routing protocols are basically carried over from wire internet, which do not consider the wireless broadcast nature. We need to consider both the physical speed quality and MAC congestion in routing. And so that the packet can use a high link speed, high speed link, and also avoid this congested area. And also the inefficient MAC and self-interference effect for TCP flows further degrade the system performance. These problems have to be solved in order to achieve good performance in ad hoc networks. My work is on these two problems and with a focus on system architecture and protocol aspects. As we know, when there are problems, there are opportunities. These problems provide an opportunity for our research. The approach we are taking for the research is based on a hierarchical architecture and cross-layer adaptation, which include a three-tier hierarchical network and a dual radio forwarding node, and separate allocation of frequency bands to each tier of the network, adaptive routing framework, and a cross-layer routing. Now let's look at the scaling problem in a flat ad hoc networks. In a peer-to-peer communications, the Gupta and Kumar's work has proved that the throughput per node can only of a flat network can only achieve 1 over square root of n, given n is the number of ad hoc nodes in the network. And notice that in addition to this peer-to-peer network, most of the applications involve traffic going to and from the internet. And in this case, the scaling problem becomes more difficult due to the traffic bottleneck around these gateway nodes. And the scaling problem can be partially solved by introducing a MAC layer clustering. In this network, there are 4 clusters, which each have a cluster head, which take care of the channel access and localized control in response to network state changes. But the throughput gains achieved by using clustering is limited. Therefore, a new approach is used to introduce an infrastructure node to the ad hoc network and use infrastructure as the shortcut for traffic over long distance. However, in addition to achieve significant improvements on the throughput, the density of infrastructure nodes required is high. And Liu and Tosley's work proved that in order to achieve a linear scaling of throughput, the infrastructure nodes has to be growth asymptotically fast and the square root of the ad hoc nodes in the network. I forgot, that's the 2-tier network in which the access point as the infrastructure node is connected to the internet. These considerations motivate our solution of a multi-tier hierarchical hybrid network. In this architecture, there's a k-level hierarchy with k-1 tiers of radio nodes and a top tier of access points. Access points provide access to the internet and interconnection with the internet. And a key component of this architecture is the radio forwarding nodes, which is located in the multiple intermediate tiers and used to reduce the required wide access. The forwarding nodes are equipped with 2 or more radio interfaces, which permit them to handle traffic, avoid interference with different tiers using orthogonal channel assignment. And this multiple interface forwarding node also enable multi-radio, multi-frequency scaling. The lowest tier is very simple and with limited routing capability. As shown in this figure is a strict hierarchy. In practical systems, a radio node in a given tier can communicate will pass on the same tier or can go up or go down to 1 or more tiers, whichever is preferred by the routing protocol. In this sense, a non-strict hierarchy is provided to is allowed to provide flexibility. The radio independence means that the different radio technology can be access technology can be used for different tiers. Having discussed the conceptual system architecture, now let's look at the 3-tier AO2.11 based network. In this network, some nodes without power control constraints, for example, the laptop or this host, either fixed or mobile, can serve as a forwarding node to extend the wireless LAN coverage. And in this system, the discovery procedure and multi-hop routing is required. And our system evaluation coming in the next slides will be based on the 3-tier AO2.11 network. This is the protocol architecture of the AO2.11 3-tier network given in the last slide. Taking a mobile node as an example, the protocol stack consists of the AO2.11 MAC, 5 MAC discovery and routing. And this is the main protocol stack. Therefore, the system and protocol design coming with this proposed architecture include MAC discovery and routing. In my work, I'm working on the system scaling for system design and also the adaptive routing in this, which will be covered in the rest of this talk. Now let's briefly look at the background and notation. There are two important results on the flat and 2-tier wireless network, as we have discussed them before. And in our analytical model, we use the protocol interference model. And given the transmission range R, a successful transmission is defined here. And a slotted packet scattering is used to eliminate the transmission collisions and interference. And the throughput capacity is defined here. And I have proved the aggregate throughput capacity of the 3-tier network we proposed. And the aggregate throughput counts all the throughput of all the nodes in the network.
Can you explain in words what vertical interference model is?
It means that if we have a transmission R, and in order to have a successful transmission, the node gets the transmission from node J to, from Xi to Xj. If their range is smaller than R, and also there's no other nodes have a closer transmission range, and then the transmission is successful. That's called the protocol interference model. And there's another interference model who called the physical transmission model, which calculate the SNR. That's another approach. This is the 3-tier hierarchical hybrid network, as we already discussed before. The network consists of 3 types of radio device: access point, forwarding node, and mobile node. And each access point and its associated forwarding node and mobile nodes form a cluster. We are going to show this 3-tier hierarchical hybrid network help improve scaling properties while reducing wide infrastructure cost. We consider both the peer-to-peer traffic and internet traffic flows in the study. Now we suppose there are NA access points, NF forwarding nodes, and NM mobile nodes in a disk of area 1 meter square. And mobile nodes are randomly distributed, and access points and forwarding nodes are regularly placed. The low-tier nodes associate to high tiers and form, and the hierarchy is constructed by forming clusters and subclusters. In this network, the mobile node and access points are data source and sinks. Forwarding nodes only relay traffic between these other two tiers. The wireless channel is divided into 2 sub-channels. One is used to transmissions to and from the mobile node, and the other is for transmissions that does not involve mobile nodes. In order to participate in transmissions on both sub-channels, the forwarding node have to be equipped with dual radios. We can see the traffic pattern, the internet traffic, and the local traffic here. And the deterministic routing is used in this work, which will be discussed later. And this shows a low-tier transmission. And for the high-tier transmission, depending on the relative locations of the communication peers. The local traffic in the high tier can be either inter-cluster or inter-cluster. Now we define the routing for the internet and inter-cluster local traffic as the packet, such kind of packet always goes through the infrastructure nodes. And this network with such a traffic pattern can be modeled as a random aggregate network. And I have proved that the capacity is of order of the bandwidth allocated to the system. Also, the traffic distribution over the network is proportional to 1 over x, where x is the distance to the center of the disk. And we skip the derivation here. For the intra-cluster local traffic, the packets are relayed by forwarding nodes using ad-hoc mode. Since these two tiers of transmissions use orthogonal channels, so there's no interference between them. So we can consider capacity separately for two tiers of transmissions. Now we give the aggregate low-tier capacity result here. And we don't go into the detail of how to derive it. And the low-tier capacity increased linearly with the number of forwarding nodes and the low-tier bandwidth. And the low-tier transmission range has to be satisfied this condition. Now we suppose each mobile node carries traffic of lambda bps on an average. Then we have this equation, which implies that the system's scaling behavior only depends on the traffic carried by all the mobile nodes instead of their exact number. This is an improvement over the relative two-tier network because we don't need to consider the number of mobile nodes in the network, the ad hoc nodes. This table gives the high-tier capacity result. According to the scaling region of the number of access points, in terms of as a function of number of forwarding nodes, we have two scaling regions. One is when NA grows asymptotically faster than the square root of NF. We have this capacity result. This is not a good result because its scaling behavior is not good. And for this scaling region, when NA grows faster than the square root of NF, the high-tier capacity has a linear relationship with the number of access points. This is a good result because the improvement by adding access point is significant. With this expression, we may wonder if we can increase the capacity further with increased number of access points. It may not be true because this only gives the lower bound of the scaling region, and we want to find if there's the upper bound for this region. From our derivation, we found that the high-tier transmission range has to satisfy these two conditions. And these two conditions imply another relationship between the number of access points with the number of forwarding nodes. This is the upper bound we are looking for. Therefore, combined together, we get the refined scaling region for the linearity to hold. Because the number of forwarding nodes can be much less than the mobile nodes, so the linear scaling can be achieved with much less of access points relative to the two-tier network.
So what's the rule for the number of forwarding nodes as a function of the number of nodes? Does it matter?
I'm sorry?
Does it matter how many forwarding nodes you have as a function of nodes? The size of the network?
The size?
Does it matter how fast NF grows?
The growth? I didn't get it.
Explain more about the relationship
To NF to the size of the network.
Yeah, that's because the transmission range. When the size of the disk is determined and the density of these nodes is changed, and the transmission range has to be satisfied these conditions. to maintain this linearity. So, and this condition would imply this.
So I tend to think of going from the bottom up, right? Like you start with some area, the number of...
Yeah, start from a determined size.
Like the
and
bottom tier sources.
and then put the number of nodes, and then decide the transmission range.
Okay.
And
So you fix a unit disk, right?
yes,
So then the transmission range is shrinking.
yes, when the density increase.
And the number of forwarding nodes relative to the number of nodes.
Relative to the number of access points.
Well, what about the number of nodes?
Number of
Bottom nodes.
the bottom nodes, because it used a separated subchannel, so it doesn't matter. Because the forwarding node used as the aggregate tier to aggregate the traffic of the bottom nodes.
So the number of bottom level nodes is proportional to the number of forwarding nodes?
This is for the low tier capacity, which is related to the number of the bottom nodes. But actually, it's not related to the number of bottom nodes. It's only related to the total traffic carried by these bottom nodes. So that's the improvement that we can achieve with adding an intermediate tier of forwarding nodes. Because we aim to decrease the infrastructure cost as much as possible, which is the design principle we are going to take here. Did I answer your question?
I'll think some more, maybe I'll ask you again later.
Okay. Okay. So the main result is the high tier capacity increased linearly with the number of access points. It's the high tier capacity in this scaling region, and we can adjust the high tier nodes or the bandwidth allocated to different tiers to accommodate the network traffic and maintain the scaling property, which are the system design principles for such the proposed network. Okay, let's look at the system evaluation. We know that the overhead of MAC and routing might be high and would tend to degrade system performance and affect the scaling property. Because we made the assumption about a perfect MAC and routing in our analysis, we may ask this question: do these analytical results hold for system simulations and with realistic protocol and traffic assumptions? We are working on this question on this part of work. For system simulation, we have estimated potential increase in performance with the three-tier hierarchy and examined the scaling properties in terms of some key parameters. We use NS2 simulation model. All the nodes use IEEE 802.11 MAC DCF. We assume a static discovery protocol to compute and maintain a well-balanced hierarchical architecture. Actual routing protocols, including DSR, AODV, and DSDV, has, with appropriate modifications, has been applied to the hierarchical network. In this simulation model, we have modeled three types of radio devices corresponding to access points, forwarding nodes, and mobile nodes. We have implemented dual radio forwarding nodes with two network interfaces. The hierarchy is constructed as follows. The ad hoc nodes are randomly distributed in the network. Access points are placed in a regular pattern, and the nodes associate to a nearest AP based on the geographic distance and form clusters. Therefore, in this scenario, there are four clusters, with one AP located at the center of each cluster and almost the same number of nodes, ethyl nodes, and traffic flows in each cluster. We consider internet traffic and local traffic as in the analysis. Use the exponential of traffic model. The baseline simulations are used to compare the system performance of hierarchical network with the flat network. The simulation parameters are given here. In particular, we have 4 forwarding access points and use a low mobility scenario. In order to measure the performance achievement by adding a hierarchy, we use single frequencies here. The corresponding flat mesh network is set like this, and we measure this performance metric. These figures give the simulation result. It is observed the throughput increased at a factor of about 4, which is consistent with the number of access points we deploy in the network. The improvement of the packet delivery fraction implies that the hierarchical network can help deliver packet in mobility scenarios. The average end-to-end delay and routing overhead also improve with the hierarchical network. We carry out the simulations with another routing protocol, LDV, and observe similar results. In particular, the throughput gain is about 4 for this AP density. And the throughput gain is mainly because that first, the infrastructure serves as the shortcut for traffic so that the number of hops of the data packet delivered at the destination is reduced. The routing overhead is reduced because the mobile node does not participate in the full distribution of the routing messages. We also repeat the simulation with different number of communicating peers and observe similar results. This verifies that the throughput is independent of the number of access points. Now we want to take a closer look at the scaling properties of the hierarchical network. First, let's look at the impact of node density. In this network, the mobile node feed traffic into the nearby forwarding node and access points. Therefore, the forwarding node and access points form a core ethyl network. We want to look at the relative density of access points and forwarding nodes. We also look at the impact of traffic pattern represented by different fractions of internet traffic. A regular spatial model is used in which access points and forwarding nodes deploy regular placement. In order to prevent isolated area, we use the forwarding node to cover the entire network and change the number of access points to determine the right number for the system to scale. The simulation had been carried out for 2 simulated regions with identical forwarding node density. And this is network scenario with 36 forwarding nodes and 2 access points. Mobile nodes are randomly distributed in the network, but not given here. First, let's look at the simulation result with DSR. This figure shows the normalized throughput as a function of the overload. We observe there's a big gain with 4 access points. And after that, the throughput increased at a slower rate. This is the capacity with different number of access points, clearly showing that the capacity increased almost linearly before the number of access points is increased to 4. And after that, there's a saturation phenomenon after that. Therefore, the simulation result is consistent with the linear property we discussed before. And 4AP is a good operation point because it provides a new maximum throughput with a modest infrastructure cost.
So on the left-hand slide of the previous thing, like the purple curve at the top is...
It's 12 for APs, 12 APs. Yeah.
They just go in order, and the next one is 9.
Yeah, that's...
They go
oh, sorry. Oh no, this one is
The top
9.
one is-
This is purple is 9. The black is 12.
So why is 9 better than 12?
Because 9 provide almost the full coverage. The access point provide the full coverage over the network, and the 12 access points increase the interference between neighboring access points, which will have decreased this factor decrease the throughput. Because we don't change the transmission range in our simulation, which is different from the analysis. If we shrink the transmission range when we increase access points, it will provide better. And for the simulation with DSDV, the fraction of internet traffic is adjusted. Now let's look at the impact of traffic. We can observe the throughput grows as the internet traffic fraction increased from 20 to 100%. And for the large number of access points. But for the one AP case, it is the reverse. And for the impact of node density, these four curves have the similar behavior as the DSR case given in the last slide, which shows that throughput grows linearly with the number of access points only in the scaling region. And the saturation phenomenon studied at 4 APs or for all these curves, showing that we cannot achieve a linear improvement if the number of access points is not bounded.
Or relative to the analysis, how many FNs do you have?
I have 36 forwarding nodes.
To go back to the bottom, we can say it's consistent with the analysis. How do you assess them?
Because the analysis only gives the asymptotical result, so and the factor for this relation is hard to get. So in our simulation, we show this tendency for saturation. I think that's the simulation can verify. And for the exact value is hard to from the simulation, because we cannot make the number of ad hoc nodes go to infinity. That's what's showed in the analysis.
I think the order of magnitude you're getting is of the square root.
Yeah.
Below the constant you have is less than 1 if you would replace the square root law.
The constant might be different for different scenarios.
But you have the same feature that you're using the same sort of coverage area, right? The same transmission radius.
Yes, yeah.
For the protocol model.
Yeah.
So like, is it for the right answer because it's providing, like the way in the previous example, 9 was better than 12,
Mm-hmm.
right? Is for the right answer because of the size of this coverage area.
Mm-hmm.
Like if you made whatever the area of the box is, that everything is in 10 times bigger, would 4 still be the right answer? Blow everything apart by a factor of 10, you still get or 100.
It's I think the transmission range is a factor, and also when we look at the network scenario, I think instinct feeling is that the 12 AP is much more, but for the exact effect,
12 APs is much more.
yeah, it's
Much, better.
no. For serve this number of nodes, ad hoc nodes in this network.
So what made you say, like the analysis says you want somehow the radius to shrink by the square root of the number of forwarding nodes? Like there's but instead when you did your experiment, you said let's just leave the transmission radius fixed and not shrink the transmission range as things get fixed? Why not do the experiments with a shrinking transmission range? And density?
It's hard to determine how much we should shrink because the transmission range obtained in analysis is also a order something. It's not the exact number. So it's hard to get the instruction from the analysis how to set this parameter in the simulations. And the goal of the simulation, I think, is to provide the design guidance for such network, but it's very hard to very exactly compare with the analytical results, because such kind of simulation work have not been done before.
So there were like sort of asymptotic sort of results about sort of with percolation theory, right? That say, there are these sort of critical threshold where the network sort of disconnects, right?
Yeah,
You choose
yeah.
the range too small. And like if you set a range a little bit bigger than that threshold, is that the kind of range that would be appropriate? Like is there some connection? Like it seems like the results really depend on the transmission range.
Yeah, the transmission range should be depend on the density, node density. But still, the work you mentioned about the connectivity of the network is also asymptotical behavior, not the exact number. So, probably you can give me some suggestion on how to set these parameters on simulations.
I mean, it sounds like you're sort of telling people this is an important hard problem and somebody ought to solve it, right? Yeah, so let's keep going.
Okay, now so far our simulations use single frequency system. Now let's look at the dual frequency system. In the analytical, the results show that the capacity has a linear relationship with the bandwidth allocated to the system, but they don't reveal explicitly how the bandwidth allocation affects system capacity. For this purpose, we have conducted additional simulations simulations to investigate this issue and obtain some guidance on system design. In the dual frequency system model, both the access points and forwarding nodes are equipped with dual radius, and the wireless transmission at the low tier and high tier has been demonstrated in this figure. In this model, the packet chooses the same routes as in the single frequency system. Our problem is the bandwidth allocation. The bandwidth should be allocated to two tiers in proportion to their traffic load. And the MAC throughput can be used as a measure as the traffic load, which is defined as the total number of bits sent by all nodes per second, including the forwarding nodes. According to this definition, the max throughput can be obtained by the product of the end-to-end throughput and the average hop count. Therefore, the bandwidth allocation depends on the ratio of the average hop count at the two tiers. We remember this feature. Therefore, we can get this ratio from the single frequency system. And according to the routing algorithm, the high-tier transmissions are always one hop. Therefore, we can achieve the average hop count at different layer at low tier for different type of traffic. And finally, we can the bandwidth allocation can be decided by the average hop count in the single frequency system and the ratio of the local and internet traffic. And we have introduced the method. We are going to allocate the bandwidth to different tiers. Now take the previous network scenario as an example. We measure the average hop count at 2 tiers for different number of access points and given in this table. According to these ratios, we define 3 kinds of bandwidth allocation ratios given here. And the single frequency system, since it can be considered as an imperfect type of dynamic allocation via the MAC protocol, it is taken into account for comparison purpose. Now let's look at the single frequency system. The capacity of one AP is limited by access to the wire network, and there's very little gain from doubling the bandwidth from 1 to 2 bps. The throughput gain is better for the 4 and 9 AP cases, but still not significant. This can be attributed to the fact that the L to the 11 MAC involved significant and nonlinear overhead for MAC and routing as the data rate increase. And along with the fact that we use a small packet size in our simulations. Now let's look at dual frequency system. The 4 AP case is the practically interesting case because it provides a higher throughput with a low cost. We can observe the dual frequency assignment with the right bandwidth allocation can provide a significant gain about 30% over the baseline. For the 9 AP case, the throughput does not benefit from dual frequency assignment since most traffic is at the lowest tier. We can observe when we increase the low tier bandwidth, the throughput increase. All of this verify our approach of bandwidth allocation based on the average hop count discussed before. Let me summarize the impact of bandwidth allocation in a hierarchical system with realistic MAC and routing protocols. In a single frequency system, the throughput does not increase linearly with the bandwidth due to the increased MAC routing overhead. This motivates another scaling approach by the use of a cross-layer adaptation to decrease the protocol overhead, which has a great impact on the system scaling. And in a dual frequency system, the bandwidth should be allocated to 2 tiers according to the relative traffic load. And a static allocation can be done like this. And for more advanced approach, one is multi-channel mesh, in which dedicated channel are used to for transmissions and eliminate collisions. And when the advanced technology provide the variable bandwidth to provide enough subcarrier for transmissions in a non-interferent manner, we provide a distributed channel assignment algorithm for complete free transmissions. As in made of independent entry, we can discuss this offline. Now we talk about another scaling approach, the use of cross-layer adaptive routing. In a mobile actual network, the topology may change frequently and unpredictably due to no movement and fluctuating wireless links. And this makes the design of dynamic routing important design challenge. And while there are many results on a specific class of routing protocols, no single routing protocol performs well across the full range of parameters. Also note that the potential scaling problem we have introduced before. This consideration motivates adaptive routing and in the network such that the routing can dynamically adapt to the changing network topology and external service needs. We propose an adaptive routing framework, which allows introduction of adjustable parameters and programmer models. It also can support cross-layer mechanisms. This is the architecture of this framework. In this framework, the self-adaptation is implemented by a control loop, which collects information, make decisions, and adjust the system. The control loop consists of two parts. One part is the controlling part. We call it global policy manager here. And this other part is the control part, which include routing module parameters, and routing metrics. The global optimum can be achieved by disseminating control message over the network by either flooding actual control message or piggybacking on existing routing messages. It is apparent that the input transferred use piggyback can reduce the adaptation overhead. And in the network, the global policy manager of all the nodes can construct a distributed system and perform controlling functionality. Now let's take a closer look at the global policy manager. It is a controller to monitor the local behavior and interact with information from other nodes, analyze data according to the policy, and decide and send the control actions. And the state variable can be classified into this. And when the state variable are collected from the other layer, the PHY and MAC layer, and this framework can support cross-layer mechanisms. According to the controlled elements, the framework can support this adaptive mechanisms. According to the implementation approach, the adaptive mechanism can be classified into two approaches. One is switch selection between available routing module or metric. And we give an example of switching a routing module between TOI routing and DSDV routing. The idea behind it is that the TOI routing would fail to converge due to congestion collapse when the number of communication pairs increase in the network. While DSDV have a constant performance regardless of the number of communication pairs. We made the assumption that the packet generation rate at the source node is constant. Therefore, we can use the channel busy degree to measure to represent the number of communication pairs, and use the channel busy degree as a state variable to perform the switching routing models between these two candidates. Another implementation approach for adaptive mechanism is the integrated adaptive algorithm, which implement the control and controlling part of the self-adaptation function together in a distributed manner. This approach can reduce adaptation overhead and there's no service interruption. The adaptive routing metric belongs to the integrated adaptive algorithm. The cross-layer routing metric is also motivated by the fact that the cross-layer adaptation facilitates global optimization across different layers across the network and reduce protocol overhead, which has a great impact on the scalability. So all of this motivates a cross-layer adaptation for better scaling based on a PHY and MAC aware routing metric. This routing metric uses the physical bit rate and MAC congestion as a state variable, which are reflected in the transmission time and the channel access time. IEEE 802.11 use adaptive multi-rate according to the observed channel quality. In this figure, there's the 802.11b radio device, which experience different physical rates when connecting to its neighbors at different ranges. A long transmission range implies a low bit rate. And a path with a multiple short range high speed link may be preferred for increasing the throughput. However, the standard does not specify how to choose the physical rate. And in this work, we use and implement a SNR-based auto rate scheme, which select the physical rate based on the SNR measurements of the received packet and store this rate in a table at the MAC layer. For each outgoing packet, the device looks up the rate table and gets an appropriate rate to the next hop. In addition to the physical rate, it is possible to provide an awareness of MAC congestion to avoid bottleneck regions with high utilization. The MAC congestion can be measured by the channel access delay. We suppose an queuing system with the common channel as a server, where the packet from the nodes in the neighborhood of this common channel arrive to obtain the service. And then the access delay can be estimated by this equation. And rho is the utilization factor of the channel, which can be estimated by each node by sensing the channel occupancy. And TS is the packet transmission time. And this is the estimated channel access delay using this method measured at this node. There's a flow going on here. And we observe that the delay increase, but when the network congests, does not increase further. And this observation is useful for the MAC-aware routing metric design later. Essentially, the PARMA routing metric aims to find paths with the minimum packet end-to-end delay. And the end-to-end delay is all the times, including the transmission time, access time, queuing time, or all the links along the path. The transmission time is computed as n by the packet size over the link speed. N is the transmission time, which we set to 1. And the access time can be matched from the channel access delay. We use the method we described before. And for the queuing delay, we omit here, because a large access delay reflects a growing interface queue length. Therefore, after this simplification and approximation, we have this equation. And therefore, the PARMA metric is related to this physical data rate and the MAC congestion.
So why is it called PARMA?
It's
does it stand for something? It didn't seem to be written in the.
It's a physical MAC-aware routing metric for ad hoc network. Because
we have in the wrong place.
No wrong place.
I know Wade is that. I think Wade started the convention of naming things here after European cities.
Yeah, I think it's a city.
Yeah.
I think Dr. Ray should answer this question better.
But it is for physical PHY-aware routing metric, but it's both PHY and MAC.
Yeah.
With an M missing.
Yeah, M is missing. But PMARMA, how to pronounce?
But all the right letters are in there. I think it really worked on. You should be able to have it stand for something. It's pretty good. I was surprised that I'd never heard of anything called PARMA before.
Because
The Italian thing.
The related work is listed here. They are the cross-layer routing metric, which incorporate the state variables collected from the the MAC and file layer. MTN consider the link speed only. ETX incorporate link loss. ETT consider both these two variables, and these two incorporate the frequency diversity. And L-time link matches specified in the L2.11s have a similar expression to ETT. Consider both of these after taking away the constant factors. And compare with this routing metric, only the PARMA consider the channel access delays here. We have implemented PARMA with DSDV routing protocol. The reason for choosing DSDV is that DSDV exchange 5 MAC information periodically and enable route switch between to better ones whenever available. While with on-demand routing protocol, the route have to be used until it's broken. And DSDV, the SNR-based auto-rate scheme, which we discussed before, is also facilitated according to the SNR measurements of the received periodical updates. The cross-layer design involved challenge, and we have proposed some enhancement to the routing protocol. The first one is how to achieve a best route when we do not use the shortest path, and then the best route would come later. So we add a second routing table and accordingly adjust the route settling time. And when we incorporate the link layer and network link into the network layer, the different layers have different change variations, and the routing metric is not integral. And in this case, how to help route converge? So we propose a smooth estimator and nonlinear mapping from the estimated delay to the value we use in the routing metric. And
you're doing some sort of like a distributed development for kind of, you with a metric for the best route, right? Why do you have a second routing table rather than just like, oh, you replace the current route with the new improved route the metric says is better?
Because first, because there's a factor decides when this route can be advertised over the network. And when there's more number of hops, this time is larger, and a path with a shorter, more hops, but with a higher speed links will arrive later.
No, I know why it arrives later. That part I understood.
Okay.
But the question is, like, it sounds like you're keeping the old route around, the shorter hop, lower rate route, and you're also keeping the new route with more hops and higher speed.
Yep.
You're also keeping that in a new table. Why don't you just throw away the less good route?
Because
replace it.
Okay, because there's another variables which identify the freshness of the routing metric.
So there's something about this freshness factor for the old route that makes it you not want it.
Yeah, because the distance always trigger these periodical updates, and in this turn, all the routing metric will arrive at a particular node with the same sequence number, but with different routing metric, and for this part, I have to record in a routing table with the same sequence number, and then a new sequence routing metric with a new sequence number will come later. Will come to probably arrive before that, but you cannot say that this one is the best one, and for probably there's some change for the routing metric. If the topology or the traffic is changed, the routing metric is changed, and so you need to keep all the routing metric of a sequence number and keep in this table. the simulation model, we use NS2 simulator. And we use multi-rate L to the 11b, and the receiver's threshold and the corresponding effective distance are given here based on the two-rate path loss channel. And we evaluate these three routing metrics in our simulations and consider chain topology and grid topology. And in this chain topology, there's a flow coming from node 3 to node 7. And for the minimum hop metric, pass with two hop, one MPPS links are chosen, and for the PARMA, and this four hop pass is chosen, and there's a 2.5 throughput improvement. And the packet delivery ratio and delay also improve with PARMA metric. And in this scenario, because there's only one flow, and the MTM have the same behavior as PARMA. Now let's look at the scenario with two flows and examine the PARMA's capability of handle interfering flows. The flow one is starts earlier, and with a fixed load. And this load is used to keep the median around this flow busy enough, such that when the flow 2 starts, the congestion occurs. And we start flow 2 and gradually increase its sending rate. In this figure, we can notice this node 2 and node 32 are in the Fourier sense range of each other. And these two flows would interfere with each other when flow 2 choose the path including these links. And from our simulation result from the tray file, we can observe that the minimum hop metric always choose the switch their routes among the available 3 hop paths, shortest path. And the MTN choose this path with 11 Mbps each link. And for the PARMA metric, we will route the flow 2 around the congested area using more number of hops or slow, low rate link. And for example, this D2 on the top. The simulation result shows that the minimum hop and MTM curves start to drop from a certain point, and the PARMA keep increasing slowly until the network becomes excessively congested. And this is the how the throughput change over time. Flow 1 starts at 50 seconds, and flow 2 starts at 150 seconds. And from the first two figures, we can observe there's some link broken here and packet drops, and the performance is very bad. And for the PARMA metric, when flow 2 starts, we can observe there's a route changes over this region, and then PARMA can find a better route to avoid the congested area, and thereafter the throughput start to go up. Now let me conclude. For the hierarchical part, I developed an analytical model and proved the asymptotical capacity of a 3-tier hierarchical network. The refined scaling region and the transmission range has to be identified, and we consider both peer-to-peer and internet traffic in our work. In general, in a 3-tier hierarchical hybrid network, the low-tier capacity increased linearly with the number of forwarding nodes, and the high-tier capacity increased linearly with number of access points in the scaling region. We developed a simulation model with realistic MAC and routing protocols and verify scaling properties using detailed NS2 and system simulations. we consider the relative densities and bandwidth allocation. And both the analytical and experimental results demonstrate the value of adding forwarding node to improve scaling behavior while reducing infrastructure costs. Cross-layer adaptive routing, we propose an adaptive routing framework which supports various cross-layer mechanisms. We study a cross-layer routing metric which incorporate physical data rate and MAC congestion. Our simulation verified that PARMA helps to improve throughput and decrease congestion by selecting paths with high speed links while avoiding MAC congestion. And there's another work. For the future work, in order to improve the hierarchical network performance, there are some mechanisms we can consider. The first one is a route optimization. And we might consider packet aggregation because the hierarchical network shows a very disaggregation behavior. We can use a combine and forward to transmit the packets. For the cross-layer design, our work give an example of how to design this cross-layer routing metric in the ad hoc network and solve the different change variations between the different layers, and in order to avoid unintended effects. We need to provide a complete system architecture and protocol design for ad hoc networks with a focus on scalability, hierarchical structure, cross-layer design, global control planes, and use multiple frequencies and effective multi-hop MAC. And if these problems can be solved and addressed appropriately, the distributed mesh solution will become an important part of future wireless networks. And this gives the list of my publications. Okay, I would like to thank my advisor, Dr. Richardery, for giving me guidance and support during my years as a graduate student at InvenLab. I thank my committee for giving constructive guidance, especially thank Dr. Yes coming from California and attending to defense in a day. I thank Dr. Chappie giving me a lot of help as early as from when I prepare my PhD qualifying exams. I think Dr. Arup Acharya coming from give me guidance in my PARMA work and driving from the New York State. I also thank Ivan for sharing his expertise in wireless networking. Thank other faculty members, including the Han Liu, gave me advice for my research. I think my fellow students, Zhibing, Xiangpeng, Sachin, and Sumati, working with me in a group. Also thank the staff members in our lab, who provide such an supportive and collaborative place to work. And thank you for everything. And you have made my years in InvenLab such a precious and unforgettable experience in my life.